Hi everyone, my name is Jianwen Xie from Baidu Research. Today, I'm going to present a tutorial on theory and application of energy-based generative models, together with Dr. Yingnian Wu from UCLA. In recent years, there has been growing interest in ConvNet parameterized energy-based models. Different from existing popular generative models, such as GAN and VAE, the energy-based model can unify the bottom-up representation and top-down generation into a single framework. The expressive power and advantage of the energy-based model have launched a bunch of research works, leading to the advance of theory, algorithm, and application of energy-based models. This tutorial will provide a comprehensive introduction of current energy-based modeling and learning methodologies, and aims to enable researchers to apply the energy-based learning principle in other contexts of computer vision. We divide the materials into three parts. In the first part, fundamentals, I will present background and basic knowledge of energy-based models. In the second part, advanced, Dr. Wu will present advanced energy-based methods and explain key ideas and equations. In the third part, applications, Dr. Wu and I will present applications of the current energy-based models. We shall start from the background of energy-based models. An image is a collection of numbers indicating the intensity values of the pixels, and it is a high-dimensional object. A population of images, such as images of cats, can be represented by a probability distribution, which is parameterized by a set of parameters that can be trained from the observed data. Such a probabilistic model is useful for supervised, unsupervised, and semi-supervised learning, as well as model-based reinforcement learning. Therefore, studying probabilistic models is a fundamental problem in computer vision and machine learning. The energy-based model that we will study in this tutorial is one type of probabilistic models. We will talk about Gibbs distribution in statistical physics. Energy-based model originates from the Gibbs distribution in statistical physics. In the Gibbs distribution, X is the state of a system. For example, a cup of water, gas. E of X is the energy of the system at state X. T is the temperature. As T goes to 0, P of X focuses on the global minima of the energy function of X. Z is the normalizing constant or partition function to make P of X a probability density. The partition function is ubiquitous in statistical physics or quantum physics. States of low energies have high probabilities. In this tutorial, we are going to present energy-based model. X can be an image, a video, or a text. The negative energy function divided by the temperature T will be parameterized by modern ConvNet, f of X, where theta denotes the parameters. F capture regularity, rules, organization, and constraint probabilistically. In conditional settings, Fx acts as soft object function, cost function, value function, or critic. It actually is a softmax probability. Here, it assigns score fx to each x, as if each x is a category. Next, we will talk about frame models. In the field of computer vision and pattern recognition, the frame model was proposed for texture modeling. The frame model is a Markov random field model, or an energy-based model whose energy function is the sum of translation invariant potential functions that are one-dimensional non-linear transformation of Gabor filter responses. It assumes a dictionary of Gabor filters is given, and only learns weight theta on top of the nonlinear transformation of filter responses. These are some synthesized texture patterns sampled from the learned frame model by Gibbs sampling. The grade model tries to learn the frame model by using Langevin sampling for texture synthesis. The Langevin dynamics is a gradient-based MCMC method, which consists of a gradient ascent term and a diffusion term. Since the original frame model for texture is homogeneous, it cannot be used for object patterns. The inhomogeneous frame model is a non-stationary Markov random field model that reproduces the observed statistics of Gabor filter response at all the different locations, scales, and orientations. It used HMC for sampling. In the language of neural network, the energy function of the inhomogeneous frame models are a two-layer network, in which one convolutional layer, that is Gabor filter, is given, and one fully connective layer is learned. The deep frame model replaces the Gabor filters by VGG features and learn one fully connective layer. These are the generative examples by Langevin sampling from the learned deep frame model. Now we will present Generative ConvNet model, which is an energy-based model parameterized by modern neural network. Instead of using filters from pre-trained ConvNet, we can learn the filters from the observed data. The resulting model is the Generative ConvNet model. Such a model can be considered a recursive multi-layer generalization of the original frame model. Let X be an image. The Generative ConvNet model is a probability distribution defined on image domain. Q is a reference distribution, for example, a uniform or Gaussian white noise distribution. Z is the normalizing constant, which is intractable. The Fx is parameterized by a ConvNet structure that maps the input image to a scalar. Theta contains all parameters of the ConvNet. For the rest of the part 1 of this tutorial, I will use the Generative ConvNet as an example to present the elements of energy-based learning. In this section, we will study an important concept, which is KL divergence. Suppose we have two probability densities, P and Q. The KL divergence between P and Q is defined as the expectation of log P over Q under the distribution of P. The KL divergence usually appears in two scenarios. The first scenario is maximum likelihood learning. Given the training examples X that are assumed to be sampled from an unknown data distribution P data, we want to learn a model P of X parameterized by theta from the data by maximum likelihood. For a large number of training examples, maximizing the likelihood is equivalent to minimizing the KL divergence between the data distribution and the model. The expectation under the data distribution can be approximated by averaging over the training examples. The second scenario is variational approximation. Suppose there is a target distribution, P of target, which is known up to normalizing constant. For example, the P target is an energy-based model where negative energy function fx is known. Z is the intractable normalizing constant. Suppose we want to approximate the target distribution by a distribution Q phi, where phi is the learning parameters. We can find phi by minimizing the KL divergence between Q phi and P target. This time, we place Q phi on the left-hand side and P target on the right-hand side of the KL divergence. Because P target is accessible through fx, the above minimization doesn't require knowledge of log z. The behaviors of KL divergence in scenario 1 and 2 are different. In the MLE scenario, the learned model P theta tends to cover all the modes of the target, which is the P data. While in the scenario of variational approximation, the learned model Q phi tends to focus on some major modes of P target, while ignoring the minor modes. The reason is because the KL divergence in the second scenario is expectation with respect to Q phi. The figures displayed below demonstrate the difference between these two settings. Now we will talk about maximum likelihood estimation and analysis by synthesis algorithm. Maximum likelihood estimation is a commonly used method to train energy-based model. Suppose we observe training examples xi, which follow the unknown data distribution P data. The objective function of MLE learning is the average of the log probability density of the training examples. The gradient of the log likelihood involves an expectation term, which is analytically intractable. The expectation term comes from the derivative of the log z, where z is the intractable normalizing constant. We saw the derivation of the gradient of the log likelihood on the right-hand side. The expectation term is intractable because x is high-dimensional. Consider x is a 100 by 100 grayscale image, and each pixel can take a value from a region from 0 to 255. The image space is too big to do summation over x for computing the expectation according to the definition. Therefore, it has to be approximated by Markov chain Monte Carlo MCMC method, such as Langevin dynamics or HMC. To be specific, we can sample x tilde from the model distribution and use the sample average to approximate the expectation. Now, we shall study Langevin dynamics, which is a gradient-based MCMC method that is important and useful to compute the gradient of the log likelihood. For high-dimensional data x, sampling from the distribution P of x, which is in the form of energy-based model, requires MCMC, such as Langevin dynamics. The Langevin dynamics is a stochastic gradient ascent algorithm that finds data x to maximize the function f. Larger f corresponds to larger probability density. Delta t is the step size, and ET is the Gaussian noise term for randomness. As the step size goes to 0 and the number of steps goes to infinity, the distribution of x will converge to the target distribution P of X. There are different implementations of the Langevin sampling. First, for the persistent chain, we run finite step MCMC from the synthesized examples generated from the previous apple. Secondly, the contracted divergence runs a finite steps MCMC from the observed examples. Third, if we run finite step MCMC from Gaussian white noise, this will lead to a non-persistent short-run MCMC. This is a full description of the MCMC-based MLE algorithm for energy-based generative model. At each iteration, we first sample synthesized examples from the learned distribution by MCMC, and then use the training data and the synthesized data to compute the gradient of the log likelihood, such that the model parameters can be updated by gradient-based learning algorithm. The learning algorithm tries to match the synthesized example to the data in terms of some statistics. Such a learning and sampling algorithm is called analysis by synthesis algorithm. We are going to talk about adversarial self-critic interpretation. Here, I want to show you the adversarial interpretation of the energy-based learning. The update of parameters theta is based on the gradient of the log likelihood, which is the difference between the observed statistics and the synthesized statistics. If we take out the gradient sign of the summation operator and define a value function v, which is a function of the synthesized examples x tilde and the learning parameters theta, the gradient of the value function is equal to the gradient of the log likelihood. We can easily find that the learning and sampling algorithm actually play a minimax game. In the learning step, the algorithm finds theta to maximize the v, and in the sampling step, the algorithm finds x tilde to maximize the score function f, thus minimizing the value function v. Please also see part 2 of the tutorial for adversarial contractive divergence for EBM. The analysis by synthesis learning algorithm is a mode-seeking and mode-shifting process. Here is an illustration. The red curves and blue curves represent the negative energy landscapes of the true model and the learned model, respectively. The red crosses indicate observed data, and the blue circles indicate the synthesis data. Figure 1 is the mode searching by Langevin dynamics, which finds high-score modes in the landscape of the model, and placing the synthesized examples around the found modes. After that, the algorithm shifts the high-score modes toward the observed examples, which is shown in Figure 2. Figure 3 is the mode tracing, which researches the high-score modes in the updated landscape of the model. Figure 4 is the mode matching, where the modes in the learned landscape eventually match the ones in the data distribution after a few iterations of mode searching and shifting. Now, we are going to talk about short-run MCMC for EBMs. Given an energy-based model P of X, E is the intractable normalizing constant. Fx is the negative energy. Theta are the parameters. The maximum likelihood learning of the energy-based model P of X requires the MCMC sampling, such as Langevin dynamics. to approximate the gradient of log likelihood. The Langevin dynamics is an iterative algorithm where each step consists of a gradient ascent that maximizes the function f and the noise term serving as Brownian motion. The model P of x can be highly modeled, and the gradient-based MCMC may get trapped in local modes, so that different Markov chains initialized from different starting points do not mix. We now consider the learning algorithm based on short-run MCMC. To use a short-run MCMC, we initialize the Langevin dynamics from a fixed initial probability, P0, and run a fixed number of k-steps. The resulting marginal distribution of sample x after running k-steps of MCMC starting from P0 is denoted by Q of x. Since the short-run MCMC is non-convergent, so Q of x is not equivalent to the target distribution P of x, and x is highly dependent to its initialization. Therefore, the k-step short-run MCMC can be considered as a latent variable model or a generator with initialization z as latent variables. Here we use M to be the transition kernel of k-steps of MCMC toward the target distribution. The short-run MCMC can be written as x equal to M of z, where M is nonlinear mapping and z is latent variables following the distribution P0. This figure shows some generative examples by short-run MCMC. Training the parameters of the energy-based model with the non-convergent short-run MCMC is no longer a maximum likelihood estimator, but a moment matching estimator that solves the following estimating equation, which is the perturbation of the MLE estimating equation, where we just replace the model P by the short-run distribution Q of x. In part 2, we will present methods to improve sampling and reduce bias due to perturbation of MLE, or to avoid sampling. Now, I want to show you how to understand the learning behavior of the short-run MCMC. Let's consider a simple model where we only learn top layer weight parameters, theta. The blue curve illustrates the model distributions corresponding to different values of parameters. The black curve illustrates all the distributions that match the data distribution in terms of the expectation of hx. The hx is a feature vector of x. The ideal MLE solution, which is the green dot, is the intersection between the blue curve and the black curve. The red dotted line shows the MCMC starts from P0 and runs toward P with theta hat MME. MME means moment matching estimator. But the MCMC stops after k steps, reaching Q with theta hat MME, which is the learned short-run MCMC generator. Even if the learned P of theta may be biased from MLE, the resulting short-run MCMC is considered a valid model in that it matches the data distribution in terms of expectation of hx. As we mentioned before, the short-run MCMC can be considered a latent variable model or generator. Therefore, it can be used for reconstruction or interpolation. In the top figure, we show that with the short-run MCMC generator, we can find latent variable z for each images. and perform linear interpolation on the latent space. The transition in the top figure displays the sequence of generation with interpolated Z. In the bottom figure, we saw that the short-run MCMC generator can perform reconstruction by finding Z to minimize the reconstruction error. Both of these experiments validate the learned short-run MCMC is indeed a latent variable model. Now, we will talk about equivalence between EBMs and discriminative models. In this section, we will show you the equivalence between the energy-based model and the discriminative model. We will first introduce the discriminative model. Let X be an image and Y be a label of X. Suppose they are C categories. The probabilistic model P of Y given X for classification is in the form of softmax classified, where F is a deep net and theta denotes all parameters of the network. For different category C, the network F outputs a different value. Therefore, we use the subscript C to index the F. Different C can share a common body of the network F and only have a different head layer in F. This softmax model can be rewritten to an energy-based form with Z representing a normalizing constant. Since the space of C is small, the computation of Z is tractable. We can learn the discriminative model by maximum likelihood. The gradient of the log likelihood with respect to the parameter theta involves an expectation terms due to the derivative of log Z. The maximum likelihood minimizes the KO divergence between the conditional distribution of data and the model. The calculations are analogous to the calculations for the energy-based generative model. The difference is that for the discriminative model, the normalizing constant Z and the expectation are summations over Y, where Y belongs to a finite set of categories. While for the energy-based generative model, the normalizing constant Z and the expectation are integral over X, where X belongs to a high-dimensional space. Therefore, the expectation in the energy-based generative model cannot be calculated in a closed form and has to be approximated by MCMC sampling, such as Langevin dynamics. A special case is binary classification. They can take either 0 and 1, and the model is a nonlinear logistic regression model. Here I want to show the EBM and discriminative model are equivalent to each other. A more general version of the energy-based model is of the form of exponential tilting of a reference distribution. Let X be the data. Qx is a reference distribution, such as uniform distribution or Gaussian white noise distribution. The original form of the energy-based model corresponds to Qx being a uniform distribution. If Q is a Gaussian distribution, then the energy function is negative f plus x squared divided by 2. Even though Q is usually taken to be a simple known distribution, Qx can also be a model. We call it a based model or a backbone model. And P of x can be considered a collection of Q of x. And the Fx is the collection term. We may call Px the energy-based collection of the based model Qx. We want to show that this exponential tilting leads to a discriminative model. We can treat the P of x as positive distribution and Q of x the negative distribution. Let y be a binary variable which can take value from 0 and 1, and y is label of the distributions. We also assume a prior probability of y equal to 1 is rho, so that the prior probability of y equal to 0 is 1 minus rho. P of x given y equals to 1 is our distribution P of x, and P of x given y equal to 0 is the reference distribution Q. According to Bayes' rule, the model can lead to a discriminative model, which is a logistic regression. More generally, suppose we have C categories. Each category corresponds to one energy-based distribution. F with subscript C are C networks that may share the same body but with different heads. Suppose the prior probability of category C is rho C. Then we can derive a conventional softmax classifier from the energy-based models. Conversely, if P of y given x is of the form of softmax classifier, then P of x for a specific category will be of the form of exponential tilting. Therefore, the discriminative model and the EBM are equivalent to each other.